It's a sphere that's cut with parallel planes, parallel to the xy plane, at z equals +1 and z equals -1. Since we don't want points in between, we don't want rho to track between 0 and 2, because that would be a solid volume, not a surface. And what I'd essentially do is I'd be forming this right triangle. Although it looks like it might not be a 45, 45, 90 right triangle, I spend most of my day, every day for the past 6 years owning my business, helping students get better at math, figuring out how to communicate things in a clear and concise and useful way. Today you're gonna see what looks like a normal problem, but there's nothing usual about it. What is it? Find out today on High Peak Education. Let S be the part of the sphere x squared plus y squared plus z squared equals 4 that lies between the planes z equal to 1 and z equal to -1. Sketch a graph of S. Explain if the following vector valued functions are valid parameterizations for S. Part A, the idea is that the way you draw it is just go ahead and draw a sphere. What would the radius of the sphere be?
A radius of 2.
Exactly. Capturing the essence of what you see here on Desmos. It's a sphere that's cut with parallel planes, parallel to the xy plane, at z equals +1 and z equals -1. And then the result is that you kind of get that hamburger type shape where it's flat on top, flat on bottom, rounded on the sides. Okay, let me try to be clear about this. The screen itself, of course, or any piece of paper is always basically two-dimensional when we're drawing it. So we have to make it the drawing sort of perspective-like. If you have the XY plane straight in the plane of the screen or the paper, then you can't necessarily see that third dimension coming out at you because, for instance, on Desmos, if you click the XY plane button, you'll see that it's going to look just like a circle of radius 2 centered at the origin. Then it says part B, explain if the following vector valued functions are valid parameterizations for S. So we have r of t being 2 cosine t, 2 sine t, comma t, for t between 0 and 1. Then we have r of theta and phi being 2 cosine theta sine phi, comma, 2 sine theta sine phi, comma, 2 cosine phi. Theta going between 0 and 2 pi, and phi going between pi over 4 and 3 pi over 4. And then finally, the last r vector of rho, theta, and phi would be rho cosine theta sine phi, rho sine theta sine phi, and rho cosine phi. Rho between 0 and 2, theta between 0 and 2 pi, and then phi between pi over 3 and 2 pi over 3. When I said R in each of those, R vector, when I named off the components, those are components of a position vector from the origin. First question. Given that there's only one input parameter t on part B, Roman numeral (1), what would it sketch out in 3 dimensions? It's actually going to make a helix, because as we progress from -1 to 1, it's going to produce a helix around the z-axis. Another thing to note is that even though the x and y will sort of go along the edge of this, it'll only go on the outside edge just along a single curve. So what I'm saying is, if you plug in, let's say t equals -1, so you have r at the start, you're going to get 2 cosine of -1, comma, 2 sine -1, and then -1. From the space curve plotter, it looks like this, and then for the parametric curve, it looks like this. So you can just see that it's a space curve. It's still in 3 dimensions, but it's just simply a curve. Hey, thanks for checking out High Peak Education. Do you need some one-on-one guidance? Go to our Calendly link and book a grade boost game plan. Or if you're studying for a standardized test, for a score soar game plan. At highpeakeducation.com, you can click book now or see our Calendly page. Okay, let's get back to today's video. Imagine I'm gonna draw with phi minimum equaling pi over 4. So that's gonna be pi over 4 is gonna be a 45-degree angle. So I'm gonna start here at the origin. I'm gonna go out to this point here, because that right there would be phi minimum, and that phi minimum is pi over 4, 45 degrees. And what I'd essentially do is I'd be forming this right triangle. Although it looks like it might not be a 45, 45, 90 right triangle, I think it actually will be, because this is drawn such that phi min is meant to be pi over 4. So sometimes when you use these 3D plotting software, it's easy to have it look distorted. What I have for this right triangle here, this is true as drawn. So as drawn is meant to be pi over 4. But the thing is, our surface, but from the origin up to some point of interest, say right there. So this is a 30, 60, 90 right triangle.
Yeah.
Lowercase Roman numeral 3.
Okay, I think this one is right because it accounts for both angles and the radius. And so far the bounds for everything are correct. So if P is the radius and it extends as far as it needs to go, and then the angle forms like a full 360 degrees, and the bounds for phi represent that like 30-degree angle. So that's good also.
Yeah, I would say it's correct if we only let rho be 2. There's a couple ways to explain this. So if rho is equal to 2, then we're going to get the outer spherical part of this surface, because we specifically want only the radius to be 2, because it's the outer surface edge. We don't want points in between. Since we don't want points in between, we don't want rho to track between 0 and 2, because that would be a solid volume, not a surface. The reason B Roman numeral 2 is closest to the correct answer is because there's 2 input parameters, namely theta and phi. So since there's 2 input parameters, when you sketch it out, it is going to be a 2-dimensional surface. It's like hanging a carpet somewhere out on a clothesline. It's like a piece of paper or something like this, okay? Whereas in part B Roman numeral 3, since you have 3 input parameters, it's going to be a solid region as opposed to a surface.